Hi everyone. Today we're going to continue our work looking at parametric equations in calculus. So let's start off with a little bit of review of the type of work we've been doing with group problem 1. So consider the parametric curve x of t is equal to cosine of 6t over 5 times sine of t over 5, y of t is sine of t, and we have an interval for t from 0 to 2 pi. So part A says find all the points x comma y. Now I'm going to stop right there and remind you that we are looking for the ordered pairs as our final answer, not t values. So we will have to do an extra step at the end. So we'll get to that in a moment. Where the curve has a horizontal tangent. So similar to our previous work with parametric equations, a lot of what we're doing right now is really just doing calculus A topics just with parametric equations. And so we can just review. How do you find a horizontal tangent when you have a function, right? So I have y as a function of x. I take the derivative, dy dx. How do I find where that has a horizontal tangent, right? I've set the derivative equal to 0. Okay, so this is ultimately our goal, right? Let's find dy dx. Let's set it equal to 0. All right, so to practice this question, we're going to find the t values by hand, but we will get the final answer, which remember is ordered pairs, on the calculator. Okay, so first I need to find dy dx, but since I have a parametric curve here, I have x of t and y of t, right? Both x and y are in terms of t. So I'm going to start off by finding each of their derivatives with respect to t. So what is dx dt going to be? So again, a lot of Calc A review here today. This is cosine of 6t over 5 times sine of t over 5. So I have to use the product rule. So how does product rule go? And this might be a good place to pause the video and practice this yourself. But I'm going to show you the answer right now in 3, 2, 1. Okay, so remember, product rule is the first function. So cosine of 6t over 5, I rewrote it as 6/5 t, times derivative of the second function. Derivative of sine is cosine, right? But then I have to do the chain rule, which is where that 1/5 comes from, plus the second function, which is the sine function, times the derivative of the cosine, which is negative sine, and then again, because of the chain rule, I get the 6/5 there. And so I'm just going to go ahead and rewrite this. All right, so I just kind of like to rewrite it. I like to put my coefficients in front. Okay, I'm a little picky that way. But that's my dx dt. Now, I need to go ahead and find dy dt. Okay, dy dt is going to be a lot easier because y of t is just sine of t, right? And so what is the derivative of that with respect to t? We are going to get cosine of t. Okay, so now I have dx dt, I have dy dt. I can go ahead and divide those in order to get dy dx. So a little refresher from day one, dy dx is going to equal dy dt over dx dt. So let's take my two answers from those derivatives above. Whoops, sorry, wrong tool there. Let's go ahead and write that out as one big fraction. And remember, if you're doing this on Notability, copy and paste is, as always, your friend. So we get cosine of t over 1/5 cosine of 6/5 t times cosine of t over 5 minus 6/5 sine of 6/5 t times sine of t over 5. Okay. Now, that's a very complicated looking derivative, but we can actually keep on doing this by hand. Remember, our goal is to figure out where dy dx is equal to 0. Well, in my case, dy dx is a big old fraction. How do I make this fraction equal to 0? Well, how do you make any fraction equal to 0? You're going to set the numerator of it equal to 0, which is just the cosine of t part. And now it's good to do a little bit of unit circle review. What are some t values that make cosine equal to 0 here that are between 0 and 2 pi? Remember, we were given an interval for t to start with. So we get pi over 2 comma 3 pi over 2. And so those are my t values. So all of that work, finding the t values by hand, I think is definitely doable by all of you. Now, for the final answer, right, we're just going to take these t values and plug them back in. Finding the y coordinates is not hard, but for the x's, you'd have to do a little work, and those are not unit circle values. So we can do that on the calculator, and we get these as our final answers. Okay, now, same setup here. For part B, find all points x comma y where the curve has a vertical tangent. So vertical tangent is going to use the same derivative dy dx, except this time, right, a vertical tangent line is going to occur where the derivative does not exist. Well, again, my derivative is this big old fraction here for dy dx. How do I make a fraction not exist? We're going to set the denominator equal to 0, right? And so this part, I would say, let's just go ahead and use solver on the calculator, or you can graph this and try to find the x-intercepts. Either way, okay? Just be careful if you're using the solve function, because it might give you infinitely many solutions. You should be able to put in bounds when using solver, right? So that you only get answers from 0 to 2 pi. But let's go ahead and do that. And so we get 3 t values here. T equals 0 0.715, 2.832, and 5.313. This is also a good time to remind you that you should not use these rounded t values to then plug back in to get the final answers for x comma y, right? So whatever digits, if it gives you 6, 7, 8, 9 digits for those t values, right, I would recommend using all of them to plug back in here and get their matching ordered pairs. Okay, so again, if you want to practice that, I would recommend pausing the video real quick. Okay, but I'm going to reveal the answers in 3, 2, 1. Okay, and these are their corresponding ordered pairs that we get. All right, so hopefully this is a lot of review so far. Let's take a look at the new material we're going to talk about today. And we're going to go back to some old formulas that we've talked about, arc length and surface area. So I'm going to take us back to an old note sheet, going back to chapter 8b. Let's take a look at the day 1 notes for arc length and surface area. Okay, so we're going to start off by doing a very similar proof to what we did here to come up with the arc length formula, right? And so, what we're doing here, right, is if we zoom in on the function close enough, right, we can go ahead and say, if I zoom in really, really close, break it down infinitely small zoom in here, right, it becomes almost a straight line. Every curve does. Right, and so I can get dy and dx, and that straight line, that's my hypotenuse. I can create a right triangle out of that, right, which means I can do Pythagorean theorem, right? I'm going to replace the dy with dy over dx times dx, right? And so I'm not going to go through all the steps here because we're going to do something very similar to this in a moment, right? But this is how we got our arc length formula back in chapter 8b. So we're going to apply something very similar here. So you can write down the formula here if you want when you have it in terms of a function, right? But for a parametric curve, we're going to do a very similar proof. Okay, so again, if I infinitely zoom in on this, right, I can break up this curve into infinitely tiny little straight lines, which I will call h, right? And so I can create a little right triangle here. I should put a right angle there. I don't know why I don't have a right angle symbol. Pardon me. Okay. And so the legs there are going to be dy and dx. And so my setup here to start with is the same, right? It is Pythagorean theorem. And then I can take the square root of both sides to get h by itself. And now, similarly to what we did when it was a function, right, I'm going to multiply both dx and dy. So this is one difference, right? In the previous one, we only multiplied the dy. I'm going to multiply them both by dt over dt, which is equivalent to 1, so I'm allowed to do that. Okay, and now I'm going to kind of strategically group these terms here. So you can see I have some highlighting here. Dx over dt, that's going to get squared. This dt is also going to get squared. And then in the second grouping, dy over dt, that's going to get squared. And then this dt in the numerator is also squared. So both of these terms have a dt that is squared in the numerator, and that I can factor out. So I'm still in the square root. So I have dx over dt squared plus dy over dt squared, but I can factor out from this quantity a dt squared. And now inside of this square root, I have a product of two things because I have factored the dt squared out. So I can go ahead and rewrite this as two separate square roots. So I can go ahead and write this as dx over dt squared plus dy over dt squared. That whole thing is in one square root times the square root of dt squared. And now, why would I want to do that, right? Well, sorry, I hit the wrong tool again there. The left-hand side, or the left square root there, I'm going to keep the same. But the one on the right here, my second square root, I can go ahead and get rid of the square and the square root. Okay, and so the whole idea behind this formula, right, is I can add up the sum of all of these infinitely small h's, right, by taking this formula and doing the integral, right, across whatever interval I have here. Okay, and so this gives us the setup for our surface area formula, right? So given a parametric equation, and now this is important, and we'll see an example of this in a moment, that traverses a curve exactly once, okay? So, you could have some parametric curve set up where, t equals 0 starts here, I go all the way through, and then maybe depending on the t values, I trace back and go through the same points again. Okay, and so that would be bad, right? Because I would be doubling up over the length of that curve. So we want to make sure that as we go from A to B, as t runs from A to B, that we only trace or traverse our parametric curve exactly one time. Our arc length formula is going to be the integral from A to B of the square root of dx dt squared plus dy dt squared times dt. So let's go ahead and practice this. Okay, group problem 2. So here's my setup here. X of t is sine of t, y of t is cosine of t plus 2, and right away we notice our interval from t is 0 to 4 pi, right? Which is a problem, right? Because with sine of t and cosine, right, I am going to end up traversing this, slanted ellipse more than one time if I'm going from 0 to 4 pi, okay? So we'll do the derivatives in a moment, but in the setup for my arc length formula, right, we only have to make our bounds 0 to 2 pi, okay? So let's go back and find the derivative. So x of t is sine of t, so the derivative is cosine of t, and then y of t is cosine of t plus 2, so the derivative is negative sine of t plus 2, and then with the chain rule, the derivative is 1, so we don't have to worry about that. So back to my integral. My bounds are 0 to 2 pi, square root of my dx dt, so cosine of t squared, plus negative sine of t plus 2 squared, that's my dy dt squared. And, if you want to get rid of the negative before you type this into your calculator, that's fine, because you're squaring it, so you don't need the negative, okay? So again, good time to pause if you want to try typing this out in your calculator yourself. One quick hint when you're doing this on the TI-89, even though my variables here are t's, right, in all of my work, you don't actually have to use t, right? Remember, dummy variable inside of your integral. So you can type everything in terms of x on your calculator, and it'll still evaluate to the same answer, okay? And that answer is coming up in 3, 2, 1, and we should get 5.848, rounded to 3 decimal places. Okay. Okay, so let's keep going. Okay, and let's talk about the surface area formula. So I'll give you a sec to write that down in a moment. Let's go back to the day one notes from chapter 8b, right, where we did arc length and we did all that fun stuff with smooth curves and all that great times that we had, right, talking about frustums, everyone's favorite. Okay, so what was the surface area formula when we had a function? This is also just good review for the AP test, by the way, right? These are formulas we need to know. Okay, if f of x is smooth from a to b, then the outer surface area generated by rotating around the x-axis is 2 pi integral from a to b of our function square root of 1 plus the derivative squared. Okay, so for us, right? So the setup here is a little more complicated. Feel free to pause the video to write this down. Given a smooth parametric curve that's again traversed exactly once as t runs from A to B, the surface area of the solid obtained by revolving the curve around the x-axis is, we're not going to do a proof for this one, okay? We'll just give you the formula here, right? It is 2 pi again, times the integral from a to b. Instead of writing f of x, right, we're going to write y times, and then this part right here is my my arc length formula, which is the same thing as what we have here in the function version, right? It is f of x times, and then this square root, if we go back, right? That was our arc length formula. Okay, so it's the same idea there, right? So it is the y, right, times the arc length formula. Okay, so I know I just wrote y here, but this is your y of t function you're going to plug in there. Okay, and of course we need a dt at the end. All right, okay, so let's go ahead and try group problem 3. Find the surface area of the solid formed by revolving the given parametric equation about the x-axis. Now, if you remember some stuff from geometry, you should be able to come up with the answer for this question without doing calculus, but we'll actually use that to verify our answer in a moment, okay? So x is cosine of t, y is sine of t, so a couple of easy derivatives for us. Dx dt is going to be negative sine of t. Dy dt is going to be cosine of t. I should have mentioned our interval for t here is 0 to pi. Okay. And so my surface area formula, right, is going to be 2 pi. Don't forget the 2 pi. Integral from 0 to pi of my y of t, which is going to be sine of t, times my arc length formula, which is big square root of my two derivatives squared, okay, right? My dx dt and dy dt, each of those squared. And now, if we remember a little bit of trig, we can help ourselves out here greatly. Negative sine of t squared is just sine of t squared plus cosine of t squared. A little bit of Pythagorean identity work there tells us that what we have inside this radical is just equal to 1. And so we can go ahead and simplify this whole integral as just 2 pi integral from 0 to pi of sine of t dt. And now this becomes a simple top 20 integral. Right, so this is 2 pi times the antiderivative of sine, which is negative cosine of t. We're going to go ahead and plug in pi, plug in 0. Double negatives are going to make this plus cosine of 0. And so don't forget your 2 pi in front, right? So we're going to get 2 pi negative cosine of pi. So that's going to be negative 1, so positive 1, plus cosine of 0 is another positive 1, so 2 times 2 pi gives us an answer of 4 pi. Okay, and what I was saying earlier, right, if we remember our geometry, right, we can see from the curve here, this is a semicircle. So if I rotate this around the x-axis, this would give me a complete sphere, right? And the surface area of a sphere formula is 4 pi r squared. So 4 pi times a radius of 1, we get 4 pi, which is the same thing we got doing it the fun way, the calculus way. Okay. All right. So I think that's going to do it for us here. Okay. And I will see you next time.